In this lecture video, let's take a look at what we so-called the transformation of functions. All right. So we kind of talked about this before when we introduced the parabola. Transformation of function means the graph of the functions will actually shift, reflect, and it will actually stretch or compress. Okay. It's basically how the graph is going to be transformed from the basic or the common type of functions or the graphs of the common type of functions. So I would need you to take out your handout from 3.1. Okay. The types of basic or common functions. Okay. So basically, the picture I drew you here, those are the very fundamental graph of each one of these functions. Okay. Now, when we talk about transformation functions, okay, these pictures is going to move away, okay, from these original position. Okay, so we'll show you how to do this here just in a little bit. So let's take a look. All right, let's take a look here. Here are the summaries. Vertical shift. Okay, if you have a function, okay, y is equal to your function plus a k. If it is a plus a number or minus a number that is located outside of your function, then the graph will shift up k units or shift down so many units. Okay, so perfectly for example, so if I have a parabola, say x squared, okay, my function f of x, if it's x squared plus 3, this plus 3 is actually telling you the function will shift up 3 units, okay? The f of x is actually, this f of x is actually here, the x squared part. All right, plus k plus 3 means shift up 3 units. All right, horizontal shift means shifting to the right and left. So if it says y equal to f of x minus h. So this h, okay, is located inside the function. What do I mean by inside the function? So if I ever have a parabola that is like x minus 4 whole thing squared, okay, so this is actually a parabola. So the minus 4 here is inside. It's actually, I call it inside the function. Okay, if it's inside the function, it tells me whether I should shift to the right or left. Just like the square root function. To know where the square root function, to know where the domain will begin or end, I asked y'all before to set what's inside the square root or radical equal to 0. So you will know where the function will begin or end. Okay, that is actually also talking about the horizontal shift. So if you set it equal to 0, then x is equal to 4. So that means this function has shifted to the right 4 places because my original graph here for the square root, okay, is actually starting at 0, 0. So now I shifted to the right 4 places just by having this h inside my function, okay, inside my x squared or inside my absolute value or inside the square root or cube root. All right, plus h would mean shifting to the left so many units. All right, reflection about the x-axis or y-axis, that is depends on the signs, okay, on the leading term or what's in front of your function. Okay, so if the negative sign is in front of the function, just like when we had, negative x squared plus 3x minus 4, this negative sign here tell me my parabola point will open down, because without the negative sign, the parabola is actually open up. Therefore, with that negative sign being in front of my function, there's a reflection about the x-axis. Okay, open up, open down is actually referring to reflection about the x-axis or the vertical reflection. All right, now, if I have a parabola where this negative sign is actually inside the function, okay, if it's inside the function, maybe like negative x minus 4 squared. All right, with that negative inside the function in front of my variable x, that actually tells me it's going to be a reflection about the y-axis. Okay, at the same time, you probably seen this before. Between these two terms, I can actually factor out a negative to the outside, so that will be negative x plus 4. Therefore, that actually says this is x minus negative 4. So my vertex is actually going to be shifting, okay, to the left 4 places. All right, but the negative sign still holds in front of it. So that will still be reflection about the y-axis. So let me demonstrate with the graph real quick. I'm gonna type in simply, I'm gonna type in a regular x minus 4, parenthesis, x minus 4, whole thing squared. Okay, that's what it looked like. Right now, my h is actually positive 4, so I shifted to the right from the origin. My vertex has shifted to the right 4 places. Now, the second graph, I'm going to actually add negative x minus 4, whole thing squared. So this is remember my parabola is normally open up. So now they're actually reflection about the y-axis. Okay, that's why if you actually fold these pictures by the y-axis, folded vertically, this graph will actually imprint on the other side. Okay, that's what we mean by reflection about the y-axis. Okay, and at the same time, you see, by factoring on the negative, the vertexes now become negative 4, 0. All right. Stretch or compress vertically. All right. So that's the numerical value. Okay. That's referring to the numerical value on the leading term. If a is bigger than 1, if my leading coefficient is greater than 1, I will actually stretch vertically. Okay. If it's between 0 and 1, we talked about this before. If it's like a proper fraction, it will actually compress vertically. So when we mention about the parabola, we call them open wide or open narrow. All right. The official wording is actually stretch or compressed vertically. So I'm just going to give you a quick example. Okay. I'm going to just do a regular 2x squared, which the leading coefficient is bigger than 1. So it will be open narrow. That's called stretched vertically. Okay. You're stretching my parabola, the picture of a parabola vertically. So then the U will actually be skinnier. The U become narrower. Okay. And I explained this before, why it actually become narrow is because every X value I pick, I will actually have to go through 2 times it. I have to times by 2. Okay. So that means my Y value actually shoots up very, very quickly. Okay, so when I pick x equal to 2, it's got to square that and then times another 2. So my y value jumped from 2 all the way up to 8, and the next point it jumped to 18. Okay, it shoots up very quickly. That's why it is stretched vertically. All right, compressed. Vertically compressed, that means I actually squeeze, okay, pushing my u downward on the picture. If I push it downward, then the u will actually open wide. So let me do a 0.5 or a half x squared, and you can see it's going to be wider. Okay, compressed makes it go wide. Compressed vertically makes it go wide. Stretch vertically makes a parabola, makes a graph a little bit skinnier or narrower. Now, I didn't talk much about the number inside the function in front of the x much. Okay, it's actually very neat. Okay, if there's a coefficient, because all the example I've been giving you so far here on the side is always 1x inside the function. So if it's anything other than 1x, okay, it will actually be referred to as compressed or stretched horizontally. So let me give you a quick example here. Let me use this x minus 4 whole thing squared, for example. So imagine if I would pick a coefficient in front of my x inside the function to be bigger than 1. Let me do a 2, okay? Let me do a 2. 2x minus 4. Whole thing squared. All right, this is actually going to be compressed horizontally. What does it mean, compressed horizontally? This is the regular u. Let me go down here. Let me just graph a regular x minus 4. Whole thing squared. All right, so compressed horizontally. If I'm squeezing my u from left to the right, okay, naturally my u is going to become skinnier or narrow. That's what that means, compressed horizontally. All right. Now I hope you notice that the vertex is different between the two pictures because, go back, because this is 2x minus 4. All right. So I can actually factor out a 2 between these two terms that will actually make this -4 become a -2. So that means I only shifted to the right 2 places. Okay. But I can't factor anything out between x minus 4 other than 1. So the vertex is still going to be 4, 0, or I shifted to the right 4 places. Now, if I pick this b, this number in front of my x that is inside the function to be anything that is between 0 and 1, let's do a 0.5 again. Let me insert a 0.5 or a half. Then it means it was stretched horizontally. So basically what we're saying is pulling your u, okay, pulling your u a little bit wider. So the first function, the first picture, this u that is a little bit wider is actually pulling horizontally, pulling the u horizontally. So then it will become wider. Okay. So these numbers, okay, in front of the x actually tells you whether it is a vertical or horizontally stretched or compressed. Okay. So the b, I purposely called a different letter. The b, which is a coefficient in front of my x that is inside the function, actually tell you whether it was be stretched or compressed horizontally. All right, so let's try some example, okay? Let's try some example here. Determine the type of a basic or common function. So what type of function is this one? Okay, so that will require us to take a look at your handouts here. This problem, -2 over x plus 3 plus 5 is what type of problem? Well, it does have a fraction, so that means I'm dealing with rational functions. But which one of the two would it be? Well, the difference between the two is the exponents. Okay, if the exponents on the variable x is odd, that would be like this. If it's even, that will actually be this. So this is actually x to the first. So what you need to notice here is we can rewrite this as -2 times 1 over x plus 3 plus 5. If I rewrite it that way, I can see this is the 1 over x. Okay, so which type of basic or common function is it? It's a rational function. In the form of 1 over x. All right. You need to tell me the name of it. All right. Does the graph of the rational function shift to the right, left, or none? Okay. So to determine shifting to the right or left, that means I need to look at inside the function. Okay. So where is the inside of this function located? The inside of function, the f of x minus h or plus h is actually right here. Okay, this is supposed to be x minus h, since this is an x plus 3, so they tell me I shifted to the left 3 units. All right, where's my k? My k is always going to be outside of my function, okay? The number that is the other term, the second term, okay? Or the other term, not part of my basic graph, not part of my basic or common function. So that's referring to the plus 5 part. Okay, the negative 2 times 1 over x plus 3 is actually still going to be one term here. So the extra term here is the positive 5. So positive 5 means I will shift up 5 places, so 5 units. Does the graph of the rational function reflect about the x-axis, y-axis, or none? So reflection is looking at the negative sign. So if you look inside the function, there's no negative sign in front of x. But as a whole entire function term, I'm going to call them function term, okay, there's a negative sign up front. So that will actually be reflection about the x-axis. All right, does the graph of the rational function stretch, compress vertically? So stretch, compress vertically, that's referring to the coefficient, okay, that is outside of your function. So my a this time is 2, which is bigger than 1. So I actually stretched vertically. All right. Does it have any stretch or compress horizontally? Horizontally is referring to the coefficient in front of the x that's inside the function. So what's inside the function here, which inside the function part is the x plus 3, and the coefficient in front of it is actually 1. So it's not bigger than 1. It's not between 0 and 1. So this time would be none. I don't have any horizontal stretch. All right, let's find the x-intercept, because we're doing all these steps so we can actually grab this function here in a minute. All right, to find the x-intercept, that means we will have to set my function equal to 0. So I'm going to write it right here. That will be 0 equal to negative 2 over x plus 3 plus 5. I only got 2 terms here on the left, and my variable term is negative. Let's move over to the left side. So we can get 2 over x plus 3 equal to 5. Now, since I only got 2 terms, I think the quickest way is using cross product. So that will be 5 times these 3 terms. These 2 terms down here, that will be 5x plus 15. Set it equal to 2 times 1 is 2. So that will be 5x equal to negative 13. X equal to negative 13 over 5. All right. So before I can use it to graph, I need to kind of know exactly, kind of possibly know where is it. Negative 13 over 5 is going to be about negative 2.6. All right. So when I plot this x-intercept here in a minute, I kind of know it's going to be negative 1, 2, negative 1, 2, 3. It'll be about right here. All right. So I only got one x-intercept. I'm going to write exact answer, negative 13 over 5, comma 0. Y-intercept. Find y-intercept. Find y when x is equal to 0. So substitute 0 for x. That will be negative 2 over 0 plus 3 plus 5. So 0 plus 3 is still going to be 3. So that's negative 2 over 3 plus 5. So this is going to be negative, positive answer, I think. 3 times 5 is 15. Negative 2 plus 15. Negative 2 plus 15 is 13 over 3. So my y-intercept is 0, comma 13 over 3. Right, 15 negative 2 plus 15 is 13. 13 over 3. Let's see about where that is. It's about 4.3. That's fine. 4.3 repeating. Okay, so my y-intercept about 4.3, so that's a little bit over 4. Okay, so all right, let's sketch it. To complete my sketch, I do need to kind of still using the calculator a little bit. You know, these just give me ideas. These 2 points just give me ideas where I might be at. Plus, I kind of know ahead of time my picture. Okay, my picture is going to look something like this. Okay, and I actually have my function actually shifted. My actual function actually shifted left 3, up 5, and I'm also reflecting about the x-axis. Reflecting about the x-axis. So imagine this picture. Reflecting about x-axis means fold the paper, fold the graph along the x-axis. Okay, fold the graph horizontally. So this part will come down, this part should go up. So I kind of expect that before I even graphed it. That was the whole point of learning transformation. So we kind of know what we're looking at here, but I'm still gonna graph it so I can actually sketch this picture correctly. So that's -2. I'm gonna put my first term in the parenthesis. Okay, -2 divided by parenthesis. The x plus 3 got to go inside the parenthesis. Close parenthesis for the x plus 3, close the parenthesis for my first term, then plus 5. Voila. Okay, shift it and reflect it. So let's compare the two pictures here. Okay, look at this picture, look at this picture, right? The bottom part is going to be folded upward. Okay, this part going to come down, and this whole both piece is going to shift to the left 3 and up 5. So that will be this location. Okay, so looking at the graph, we can finish and sketch it. If you want to get yourself a couple more points, you can. But I just want to show you that the x-intercept and the y-intercept is connected by the right side here. So it looks something like this. The other side, since I'm shifted up 5 places, okay, since I'm shift up 5 places, that means my graph, okay, is actually not going to touch. This line right here, this part of the picture got to stay, okay, somewhere near the 5, where the y equal to 5. So I'm going to put it right about here. All right, we're sketching it. We're sketching it. There you go. Something like that. All right, find the restriction on the domain. All right, so let's take a look at my original function. The denominator cannot be which number? My denominator cannot be -3. All right. So this picture is not quite right up here since my x cannot be -3. I need to put this picture 1, 2, 3 to the left side of the -3. There you go, something like that. All right, so let's find the domain. So this side keep on going left, this side keep on going right. So from left to right, my domain got to be from -infinity all the way to -3 union from 3 to infinity. Now the range is a little bit tricky, okay? Because there are other things I'm not telling you right now about the range. There's something else about this vertical shift I will introduce later on. But right now, I want you to take a look at the y value. All right, as x keep on going to the right, look at the y value as I scroll down. All right, still staying at 4 point something, okay? 4.8 right now, 4.9 right now. So as x keep on going to the right, I never actually become 5, okay? My y value never become 5. Let's go the other way. Let me start it back at 0 again. If I keep on going negative, all right, this is not 5. This is actually above 5, right? 5.6 is above 5. So if I keep on going more negative, this part of the graph actually stays above the 5. All right. So that means my x value, my y value is never exactly 5. So the range of this got to be this side keep on going down, this side keep on going up. So from down and up, my range is from negative infinity all the way to 5, but never exactly become 5. Union, the other part, this part up here will be starting from 5 all the way to infinity. Okay, so there's something else about this. I'm going to show you about this vertical shift, why it's not going to equal to 5 in a different video. All right, let's try another one. This one is actually also a rational function. Okay, but this time is the even power. So this time will be this one here. So the picture should look something like this originally. But then when we add on to the transformation, when we add on to the different toppings, for my ice cream, my picture was begin to shift, begin to change. So this is going to be a rational function in the form of 1 over x squared, okay? Or 1 over, yeah, you can say 1 over x squared, that's fine. All right. Shifting to the right and left, horizontal shift. Horizontal shift means look inside. This one a little bit tricky. Look inside the function. So that will be right here. All right. So just by looking at it, a lot of students will say, well, that is actually going to be to the left 3. Well, not quite, because normally it's supposed to be f of x minus h, right? But right now, this x is actually 1x. I don't have a 1x, I have a 2x. So if I have a 2x plus 3, okay, then where have I shifted to? There are 2 different ways we can do this, okay? One way is by factoring. I'm going to make my 2x plus 3 look just like x minus h by simply factoring out the 2, because I want the h to match up, to match up. So if I factor out a 2, that will give me an x. Remember now, factoring is a division, right? 2 going to 2x, x times. What's 2 going to positive 3? 2 going to positive 3 is actually positive 3 over 2 times. 3 over 2 is actually 1.5. So I actually shifted to the left, right? Plus sign means it's supposed to be minus. So when this is a plus, that means I shifted to the left 3 over 2 times. Okay, so I can do it by factoring it out. So the x match with x. If this is plus sign, that means this is actually subtract a negative 3/2. So my horizontal shift actually shifted to the left. All right, vertical shift, that will be the k that is outside of my function. So that will be the plus 2. So that will be up 2 places. Okay, remember now my original picture looked something like this, right? So this whole picture has now shifted to the left 3/2 units and up 2. Okay, because it was sitting originally around the origin, but now it's shifting away from the origin. All right, does the graph has reflection about x-axis or y-axis? Reflection about x and y-axis depends on the negative sign. Okay, that is in front of the function or not. Since I have a negative sign in front, then that will be reflection about the x-axis. Reflection about the x-axis. So that means this entire picture reflection about the x-axis. So now my picture should look something like this now. It'll be pointing downward. All right. Does the graph of the rational function stretch vertically or compress vertically? The answer will be no. Why none? Because the 1. All right. Because this is actually, unlike the previous one, there's actually a -2. This is actually 1. So there's no vertical stretch or compress. All right. Horizontal compress. Well, the B part is the B is always the coefficient inside the function in front of the X is 2, which is bigger than 1. So I actually compressed horizontally. All right, so you can just use my wording, which one you're going to pick, compress horizontally, or you can say none. All right, reflect about x-axis, x-axis, y-axis, or none. That's why I wrote x-axis. I'm just using the same wording. All right, let's find the x-intercept again. Find x when y is equal to 0. So that will be 0 equals -1 over 2x plus 3 whole thing squared plus 2. All right, so again, my variable term is negative. So I'm going to move this term to the left side. That gives me positive 1 over 2x plus 3 whole thing squared equal to 2. All right. So let's see what's a good way to do this. If I use a cross product again, all right, 2 times this, 1 times 1. So that'll be 2 times 2x plus 3 whole thing squared equal to 1. Let me, I'm not going to multiply this out. That would be crazy. I'm going to divide both sides by 2 first. Since I only got 2 terms, I'm thinking about the square root property right now. Equal to a half. All right, take a square root on both sides. My answer is going to be 2x plus 3 plus minus equal to, positive and negative. Square root of 1/2 is square root of 1 over square root of 2. To rationalize the denominator, I need to multiply another square root of 2 over 2. So my denominator ended up to be 2. My numerator is just a square root of 2. All right, move my positive 3 over. So I get 2x equal to -3 plus minus square root of 2 over 2. Now I divide every term by 2. So my x will be, I'm going to divide this by 2. Okay, I'm going to take my first term, the -3 divided by 2, which is -3 over 2. Then say plus or minus this way. Square root of 2 over 2 divided by 2 means times the reciprocal. So that will be times a half. That will be square root of 2 over 4. All right, so that's my simplest answer. So my answer are radicals, okay? That's okay. Since I'm sketching this, I don't have to be exactly the same. So let me write down my x-intercept. -3 over 2. -3 over 2 minus square root of 2 over 4, comma 0. The other one is -3 over 2 plus square root of 2 over 4. All right, y-intercept. Find y when x equal to 0. Let me put it right here. So f of 0 equal to -1 over 2 times 0 plus 3 whole thing squared plus 2. Is that plus 2? Yep. 2 times 0 is 0. 3 squared is 9. So this is going to be -1 over 9 plus 2. -9 1 over 2 is going to be, this is 18. -1 plus 18 is 17 over 9. 17 over 9. All right, so let's sketch it real quick. Now, before I'm going to sketch this, I'm going to figure out what these numbers are. So I'm going to say -3 parenthesis negative 3 over 2 minus, all right, parenthesis square roots of 2, close parenthesis, divided by 4, close parenthesis. It's about negative 1.85, almost negative 2. All right, the other one is plus version of it. Second entry, give me what I just typed. So all I'm going to do is come here and changing my sign to a plus. Be negative 1.14. So a little bit bigger than negative 1. Ooh, these two things are tight. Okay, that's a little bit tight. A little bit over. Let me just put it right here. Okay, a little bit over. It's a little bit tight since I'm using this particular picture here. So this a little bit tight. All right. My y-intercept is 17 over 9. Let's see where 17 over 9 is. About almost positive 2. Almost positive 2. What was my vertical shift? My vertical shift is 2. So my y-intercept is right below my shift. All right, let's graph this sucker. All right, so that's parenthesis negative 1 over parenthesis 2x plus 3, close parenthesis, whole thing squared, close parenthesis, and then plus 2. All right, I kind of know it's going to open downward. So here it is. Ooh, see that real tight right here. Okay. So if I go down in my table just to look for the x-intercept, see right here, none of the y values are 0. Okay, so that tells me that, so this kind of tells me that my x-intercept is not quite negative 1, negative 2. Okay, as we can see earlier, it's very close to it, but not exactly. All right. So now let's look at the y value. I mean to show you the y value. As x keep on going to the right, the y value is never exactly 2. As x keep on going to the left, the y value is never quite negative 2 yet. So that means my picture here, all right, the right side cross over the x-axis, go, and they're going to stay right below positive 2. The other side, same thing, got to stay right below positive 2. All right. So my restriction on the domain, all right, set my denominator not equal to 0. So 2x plus 3 whole thing squared not equal to 0. Take a square root on both sides. That would just give me 2x plus 3 not equal to 0. So that would be x cannot equal to negative 3/2. All right. So my domain will be from negative infinity, right? Look at this picture, from negative infinity all the way approaching negative 3 over 2, but can never equal to it. Viewing the other side of negative 3 over 2 all the way to infinity. All right, range. We keep on saying range. So you don't have anything above, okay, above 2. But since there's nothing, so there's nothing above 2, and then my two lines, as I'm going to the right or to the left, my range is never quite exactly 2. So from down and up, I will have to say this is from negative infinity all the way up to 2, but not including 2, so I'm using a parenthesis. All right, let's try another one. So I'm just showing you different functions here. formatting out a little bit. Give it a minute. It's not letting me. Well, it's not letting me change in picture. So I'm going to just pause the video here and make a two-part video for this. All right. Thank you for watching.